Good evening. We are coming to you with a breaking situation report on the interstellar object known as 3I Atlas. New data just released from the Hubble Space Telescope has captured unexpected activity that challenges our fundamental understanding of this cosmic visitor. And tonight, we are going to walk through the evidence to reveal the truth. This is not just another update. This is a fundamental re-evaluation of an object that continues to defy every category we try to place it in. Let's get straight to the evidence. Our story begins with the Hubble Space Telescope, our most powerful eye in the sky, turning its gaze back to this interstellar wanderer. What it saw has sent ripples through the astronomical community. The image reveals a spectacular glowing halo, a coma stretching an incredible 40,000 kilometers across. But the true marvel, the detail that breaks the rules, is not the halo itself, but the object at its heart. This critical observation took place after 3I Atlas had already passed its perihelion. For those unfamiliar, perihelion is the point in an object's orbit where it is closest to the Sun. This is the moment of maximum stress, where the Sun's intense heat and radiation should have the most dramatic effect. For a typical comet, this is a moment of violent transformation. We expect to see the nucleus, the solid core of the comet, begin to crack, fracture, and fall apart under the thermal pressure. We expect to see chaotic plumes of gas and dust erupting unevenly from its surface as pockets of ice vaporize. But that is not what Hubble saw. Instead of chaos, Hubble observed a level of stability that is deeply unsettling. The data shows a sharply defined core, a single point of light that remained compact and perfectly centered within its glowing coma. There were no visible signs of collapse. There were no cracks spiderwebbing across its surface. No evidence of stretching or fragmentation that our models predict should be happening. The object appeared whole and undamaged, holding itself together against the most intense forces our solar system could throw at it. Furthermore, the material surrounding this stable core was behaving in an equally strange way. The coma, that vast 40,000 kilometer cloud of gas and dust, had expanded in a remarkably even and symmetrical fashion. It formed a smooth, balanced glow, a perfect sphere of light around the nucleus. This is not the signature of a chaotic, fracturing body. A crumbling comet would produce messy, uneven plumes, jets of material shooting out in random directions, creating a lopsided and irregular halo. The smooth, balanced nature of the coma seen by Hubble suggests that the material is being released in a controlled, steady manner, not through random, violent outbursts. This observation places us at the first major junction in our investigation. This level of stability, this calm and ordered appearance, is simply not normal behavior for a fresh post-perihelion object, especially one that has traveled from another star system. It raises a simple but profound question that underpins this entire situation report. What is holding 3I Atlas together when every law of cometary physics says it should be falling apart? The answer to that question begins not with Hubble's close-up view, but with a different perspective from another spacecraft. One that saw something Hubble couldn't. While the Hubble Space Telescope was focused on the intricate details of the object's core, another mission was quietly capturing a much wider view. The European Space Agency's JUICE probe, a spacecraft on its long journey to Jupiter, observed 3I Atlas from a different angle and distance. It's important to note that JUICE was not using a dedicated high-power scientific imager for this task. It was using its wide-angle navigation camera, a tool designed simply to help the spacecraft find its way by tracking stars. The fact that this basic camera could detect what it did is a testament to the significance of the activity it witnessed. What appeared in JUICE's frame fundamentally changed our understanding of the object's behavior. The image revealed not one but two distinct tail structures streaming away from the central glow. These were not faint, blurry smudges. They were clearly defined and separated features, each telling a different story about the forces at play. The first structure was a plasma tail. It appeared thin, narrow, and sharply defined, almost like a straight line drawn out into space. This is the classic signature of ionized gas. When a comet or active asteroid releases gas, the Sun's powerful solar wind, a stream of charged particles, strips electrons from the gas atoms, a process called ionization. Once ionized, this gas is no longer just pushed by sunlight. It is grabbed by the Sun's magnetic field and flung away at very high speeds. This creates a straight, narrow tail that always points directly away from the Sun, regardless of the object's direction of travel. Seeing a plasma tail is a definitive sign of active, ongoing interaction with the solar wind. It tells us that 3i Atlas is not a dormant rock. It is actively releasing fresh gas into space right now. Below this sharp plasma tail, the JUICE probe saw a second, heavier feature. This was the dust tail. It was visibly different, wider, more diffuse, and curved at a different angle. This shape is exactly what we expect from a tail made of solid particles, like dust and small pebbles. Unlike the lightweight ionized gas, these heavier particles are not significantly affected by the solar wind's magnetic field. Instead, they are gently pushed by the pressure of sunlight itself. This is a much weaker force, so the dust moves more slowly and drifts away, creating a broad, curved tail that generally follows the object's orbital path. The significance of this observation cannot be overstated. Seeing either a plasma tail or a dust tail is common, but seeing both, clearly separated and distinct at the same time, tells us something crucial. It proves that this is not old debris simply drifting away from a past event. The clean separation means that fresh material is being produced continuously. 3i Atlas is actively and simultaneously releasing both gas and solid particles into space, feeding these two separate tails. Now, let's synthesize these two pieces of data. We have two very different views from two different spacecraft. Hubble, with its powerful zoom, gives us a close-up look at the core, showing a calm, stable, and controlled interior with a smooth, balanced glow. JUICE, with its wide-angle view, shows us the bigger picture, a scene of motion, interaction, and energetic release, with material being organized into two distinct directional streams. This creates a paradox. The inside of the object appears steady and unshaken, while the outer regions are a hotbed of activity. This combination is extremely difficult to explain using our standard models of comet behavior. Typically, a comet that is active enough to produce both a plasma and a dust tail, especially after perihelion, should also show a disrupted core. The very forces that release all that gas and dust should be tearing the nucleus apart. We should see messy plumes, visible fractures, and an unstable tumbling rotation. Yet, with 3i Atlas, we see the opposite. The inner structure remains pristine and intact, while material streams outward in organized layers. This strongly suggests that the mechanism releasing this material is not random cracking caused by solar heat. It points to a more controlled, perhaps even a continuous process. The fact that JUICE's navigation camera, an instrument not even designed for this kind of detailed science, could so clearly detect these features means the level of activity is significant. The separation was strong enough to stand out against a crowded background of stars. This brings us to a new, more refined question. If 3i Atlas is stable at its core but is also actively producing both plasma and dust, what internal mechanism allows these two contradictory conditions to exist at the same time? If its activity is controlled rather than chaotic, what does that tell us about the true nature of this mysterious interstellar object? The answer, it turns out, was hidden in the Hubble data all along, waiting for the right techniques to reveal it. At first glance, as we discussed, the Hubble image of 3i Atlas seemed to project an aura of calm, but that initial impression is just that, an impression. In modern astronomy, an image is not just a picture, it is a rich dataset containing layers of information. When scientists applied advanced image enhancement techniques, the smooth, serene surface of the object began to reveal a complex and dynamic structure that was completely hidden to the naked eye. The techniques used are similar to what a photo editor might do, but far more precise. They used methods like unsharp masking, which enhances fine details and edges, and specialized rotational filters designed to highlight faint, linear features that might be lost in the bright glare of the coma. What these filters uncovered changed the narrative completely. The first revelation came from the very center of the coma. The inner glow, which initially appeared to be a simple, perfect circle, was not circular at all. The enhancement showed a subtle but definite tilt, a stretched brightness patterns that hinted at motion and directionality, rather than a static uniform expansion. This kind of distortion is a telltale sign that material is not erupting from the entire surface at once. Instead, it suggests that material is flowing from specific active regions, creating a lopsided distribution of brightness near the core. As the digital filters dug deeper into the data, the picture became even clearer and more astonishing. Two distinct jets of material became visible. These weren't broad, messy plumes, They were narrow, focused streams emerging from opposite sides of the hidden core. One of these jets pointed roughly toward the Sun. The other, however, pointed in the opposite direction, pushing away from the Sun and creating a rare and highly significant feature that astronomers call an anti-tail. The existence of these two opposing jets is a critical piece of the puzzle, and the key detail here is what it implies about the object's rotation. If a comet is tumbling randomly through space, or if its surface is fracturing unpredictably under heat, any jets it produces will wander, change shape, and shift direction over time. They would be unstable and chaotic. What Hubble revealed was different. The jets of 3I Atlas were aligned, narrow and clean. This geometric precision strongly suggests that the object is not tumbling chaotically. Instead, it is rotating in a stable and predictable way, locked into a steady rhythm like a spinning top. This level of controlled, stable rotation is not what scientists expect from a fragile, icy body that is actively cracking under solar stress. The position of the anti-tail made the picture even stranger. A normal dust tail trails behind an object pushed away by sunlight. An anti-tail which points toward the Sun is a geometric illusion that can only be produced under very specific conditions. It requires that larger, slower-moving dust particles be released at precise angles and at specific moments during the object's rotation. To create such a clean, narrow anti-tail requires consistency, not chaos. It implies that the activity is being driven from within the object in a regulated manner, rather than being caused by sunlight randomly tearing the surface apart. What makes this discovery so powerful and convincing is how perfectly it corroborates the wider observations from the ESA's JUICE probe. JUICE saw the large-scale result, the plasma and dust separating into two different paths. Hubble's enhanced image now reveals the source, the internal focused jets that are actively feeding those tails. We now have two different instruments, from two different vantage points, telling the exact same story. On the inside there is structure, order, and predictable rotation. On the outside there is motion that follows clear physical rules. This unified picture forces a major re-evaluation of the standard comet model. As we've said, a post-perihelion comet is expected to be unstable and unpredictable. Its surface should be a mess of opening cracks and shifting jets. In stark contrast, 3I Atlas behaves as if its activity is guided, not accidental. It's crucial to remember that these image filters did not create new data. They simply revealed what was already present, but hidden within the raw numbers of the Hubble image. These patterns are real. They were always there, waiting for the right tools to bring them out of the shadows. So our question evolves once more. If 3I Atlas is rotating with precision and releasing material in controlled, focused streams, what kind of object does that point to? And if this behavior is intentional in its structure, not a random response to heat, what does that say about the forces shaping it? This is where the investigation takes a sharp and unavoidable turn, because the object is not just behaving strangely, it is behaving in a way that someone predicted before the evidence even existed. This is the point in the investigation where the story moves from unusual observations to the realm of predictive science, one of the most powerful tools we have for understanding the universe. 3. Atlas is not just behaving in a strange way. It is behaving in a way that was specifically forecast months before the crucial Hubble image was ever taken. The prediction came from Professor Avi Loeb, an astrophysicist at Harvard University. Months before Hubble turned its lens toward the object for this follow-up observation, Professor Loeb and his team published a scientific paper with a detailed model. The model put forth a direct, though unsettling, hypothesis. He proposed that as 3I Atlas passed its perihelion, it might not just release gas and dust, but it could also release a swarm of small solid fragments. These fragments would separate from the main body and then drift under the influence of forces beyond gravity alone. According to his model, these fragments would not trail behind the object like a normal dust tail. Instead, they would be pushed sunward by a combination of solar radiation pressure and other non-gravitational effects. From this core assumption, Loeb's team ran the calculations. They predicted precisely what the sky should look like weeks later, when Hubble was scheduled to make its observation. The specifics of the prediction were not vague. The model calculated that by late November, this cloud of released material should form a bright, distinct structure. It would be shaped like a teardrop stretching roughly 60,000 kilometers in length, and it would be pointing directly toward the Sun. The paper provided specific distances, a clear geometry, and a precise orientation relative to the Sun and the object itself. It was a bold, testable forecast. And then Hubble took the image. The result was a stunning validation of the model. The feature that Hubble observed, the anti-tail revealed by the enhancement filters, matched Loeb's prediction in every single major detail. The anti-tail stretched to a length very close to the predicted 60,000 kilometers. Its position and orientation relative to the Sun aligned perfectly with what the model had forecast. Its shape followed the same narrow, tapered teardrop pattern described in the paper. This is a profoundly important moment in this investigation. Random, chaotic outgassing from a crumbling comet cannot produce such a predictable result. Typical comet activity is messy and uneven. Jets shift and fade as different pockets of ice are exposed to sunlight. Dust spreads out in wide, fuzzy arcs that change constantly. It is virtually impossible to calculate an exact future shape and position from such a chaotic system. Yet, in this case, the calculation came first and our observation follows, confirming the math. This is what scientists call predictive confirmation. It is one of the strongest and most respected forms of evidence in all of science. It demonstrates that a model isn't just reacting to data that already exists, it is successfully describing the underlying reality of a system. The model did not chase the data arrived and fit perfectly into the framework the model had already built. Critics, of course, argue that conventional cometary physics could still be tweaked to explain the result. However, that explanation struggles under close scrutiny. If the sublimation of ice alone were responsible for this feature, the pattern would be softer, wider, and far less precise. Heat-driven processes rarely produce sharp edges or stable geometry over tens of thousands of kilometers. They produce noise and diffusion, not clean, predictable structures. The implications of this successful prediction are far-reaching. If Loeb's calculations are correct, it means that at least some of the motion we see around 3I Atlas is governed by forces or mechanics that we do not fully account for in our standard comet models. This does not automatically prove that the object is artificial, but it does strongly suggest that our assumptions about how it moves and sheds material may be fundamentally incomplete. This is also where the story becomes scientifically uncomfortable for some. A prediction that works this precisely suggests that the system has an internal consistency. Something about the object behaves in a repeatable, predictable way over time, long enough for mathematics to lock onto its behavior. That inherent stability stands in sharp contrast to the fragile, short-lived, and chaotic behavior we expect from a piece of interstellar icy debris being battered by the Sun. So the question shifts again, becoming more pointed. If a theoretical model successfully predicted the exact shape, size, and position of the anti-tail before it was ever observed, what else might that model predict next? And if future observations continue to align with these predictions, how much longer can 3I Atlas be classified as just another comet? The next layer of evidence moves away from images and motion and focuses on the very substance of the object because chemistry does not lie. This is where the mystery moves from the visual to the material, where speculation must confront the hard limits of physics and chemistry. The evidence now suggests that the very composition of 3I Atlas is unlike any comet we have ever studied. Its chemical signature does not align with our expectations at all. First, let's look at the metals. Spectroscopic observations, which involve analysing the light from the object to determine its chemical makeup, have revealed a startling nickel-to-iron ratio. Within the metallic fraction of the material detected, the data shows a ratio of nickel to iron that is close to 10:1. This balance is highly unusual. It looks far more like some types of engineered alloys than the primitive, primordial mix of elements we expect to find in icy debris from the dawn of a star system. In standard comet theory, this ratio should simply not appear. Comets are formed in the cold outer regions of young solar systems, where heavy metals like nickel and iron remain locked inside tiny dust grains. They don't typically collect in large detectable amounts, and certainly not in such a strange ratio. The second and perhaps most glaring chemical anomaly is the water content. Water ice is the defining characteristic of a comet. It's the fuel that drives their activity. Comets are often described as dirty snowballs, and their mass is typically dominated by water, often making up 70% or more of the total. Yet measurements of 3I Atlas indicate that water makes up only about 4% of the material detected in its coma. This number is so low that it places the object far outside the accepted range for a typical comet. An object with such a scarcity of water should struggle to produce any significant activity at all. Yet, as we've seen, 3I Atlas is producing vast jets and releasing material over enormous distances. This creates a fundamental mismatch between its composition and its behaviour, a low-fuel engine that is somehow putting out enormous power. Standard models cannot easily resolve this paradox. The third piece of the chemical puzzle comes from its optical behaviour. Light reflecting from 3I Atlas shows a property known as strong negative polarization. In simple terms, this means the reflected light behaves in a way that does not match the light we see bouncing off typical dust or ice surfaces. Instead of scattering softly and randomly, the light seems to be interacting with a surface that is either highly structured or made of an unusually reflective material. This rare optical effect forces scientists to reconsider what the object's surface and interior might truly be made of. When taken together, these chemical clues all point in the same consistent direction. The high metal content with its strange ratio, the extremely low presence of water, and the unusual interaction with light all suggest that 3I Atlas is chemically distinct from any known comet. While any one of these details, in isolation, could perhaps be dismissed as a strange anomaly, their combination forms a powerful, coherent pattern that is very difficult to ignore. What makes the situation even more compelling is how this chemical evidence links back to everything we've observed before. The physical evidence, a stable rotating core, controlled jets, and behaviour that matched precise predictions, already hinted at order rather than chaos. The chemical profile now supports that impression. Materials rich in metals do not vaporize or fracture under heat in the same way that brittle water ice does. This could provide a physical explanation for why the core has remained so remarkably intact, even after its intense exposure to the sun. This does not mean the object must be artificial. There are still natural explanations being explored, such as the possibility that it is a fragment from a differentiated planetary body, an object large enough to have a metallic core and a rocky mantle, or perhaps material formed in an exotic stellar environment very different from our own. However, these alternative explanations require rare conditions and complex cosmic histories. They are not the simple story we usually tell about comets. Chemistry also raises a very practical problem. If water is scarce, then the immense energy driving the observed activity must be coming from another source. That is a question that cannot be answered by images alone. It demands a deeper look at how this object stores and releases energy. The next wave of data from Hubble, specifically from its ultraviolet spectrographs, may help settle this debate. These instruments can detect elements and isotope ratios that are invisible in normal light, and they could either confirm a natural, albeit strange, origin, or force scientists to expand their models even further. Until then, the chemistry of 3I Atlas stands as one of the strongest challenges to its classification. This leads us to our next critical question. If the material itself doesn't fit the comet category, then what process is powering its activity and its motion? To answer that, we must now follow the energy. Energy is the currency of the cosmos, and in the case of 3I Atlas, its energy budget simply does not add up. This is where the mystery stops being merely unusual and starts becoming profoundly difficult to explain with our current understanding. The numbers no longer match the picture we are seeing. Let's consider the scale of the activity. The jets we've observed streaming away from the object stretch across millions of kilometers of space. Producing and sustaining structures of that immense scale requires a tremendous amount of power, far more than a small, dry, rocky or metallic body should be able to generate. In a normal comet, as we've discussed, these jets are driven by sublimation, the process where solar heat turns ice directly into gas. That gas then escapes into space, carrying dust along with it. But this process is messy, inefficient, and most importantly, it is strictly limited by the amount of ice available to serve as fuel. In the case of 3I Atlas, with its apparent scarcity of water ice, the primary fuel for a comet is missing. Yet the outflows remain strong, organized, and powerful. This creates a significant energy gap that our models are struggling to close. The problem is deepened by observations in other wavelengths of light. Astronomers have detected X-ray emissions coming from the region around 3I Atlas. This radiation is not simply reflected sunlight. For a typical comet, X-rays are produced when huge clouds of escaping gas collide with the high-energy particles of the solar wind. To generate the intensity of X-rays detected requires massive amounts of gas. However, 3i Atlas does not show enough visible mass loss, enough gas and dust in its coma, to justify the X-ray levels that have been observed. The effect is too strong for the apparent cause. This leads us directly to the question of its motion, or its propulsion. Tracking data from observatories around the world shows that the object is exhibiting clear non-gravitational acceleration. This means its speed and trajectory are changing in ways that the gravity of the Sun and planets alone cannot explain. Something is giving it a gentle but persistent push. In comets, this effect is well known. It comes from the uneven release of gas from its surface, which acts like a weak natural rocket thruster. But once again, the numbers don't align. The observed acceleration of 3i Atlas does not match the amount of material we see being released. There is simply not enough visible debris, not enough exhaust, to be pushing the object that hard according to the known laws of physics. The contrast is striking. On one hand, the object behaves as if a powerful and continuous force is acting on it. On the other hand, the visible signs of that force, the gas and dust we can see, are limited. This imbalance suggests one of two things. Either we are missing a very large part of the picture, perhaps invisible material, or an unknown process, or the energy source itself does not operate like normal sublimation. Some researchers have proposed exotic chemistry or hidden internal heat as possible explanations. These ideas suggest complex chemical reactions within the object that could release energy without producing much visible gas. While such processes are theoretically possible, they remain unproven at this scale and under these conditions. Each of these proposals also raises new questions about how such a delicate system could remain stable over the immense timescales of interstellar travel. What matters most here is how this energy paradox connects with everything else we have seen so far: a stable rotating core, precise controlled jets, behavior that matched accurate predictions, unusual metal-rich chemistry. All of these clues point towards structure, order, and consistency. The energy story fits perfectly into that pattern as yet another piece that refuses to act randomly. The activity doesn't flare up and then fade away like a dying comet. It persists, it stays directional, and it remains strong even when the expected fuel source is severely limited. This stubborn persistence forces scientists to reconsider their most basic assumptions. If the power source is not ice-driven sublimation, then the entire mechanics of its motion must be re-evaluated. Acceleration without sufficient visible exhaust challenges our simplest explanations and pushes the discussion far beyond simple surface behavior. Future measurements may reveal more subtle forms of mass loss, perhaps through electromagnetic interactions or other internal processes that our current instruments can only hint at. Until that data arrives, the energy problem remains open, unresolved, and deeply unsettling. The mystery sharpens once again. If 3i Atlas is moving, shining, and accelerating with more power than its visible material allows, where is that energy truly coming from? Answering that question leads us to the final piece of observational evidence: the path it follows through space. And that path, it turns out, raises its own profound set of concerns. The mystery of 3i Atlas deepens further when we trace its journey through our solar system, because its trajectory does not look like that of a random interstellar visitor simply passing through. Instead of a single clean flyby, the object is moving through a rare and statistically unlikely sequence of close planetary approaches. It has already passed near Mars, then swung by Venus, and it is later projected to line up for an encounter with the gas giant Jupiter. While any single one of these approaches could happen by chance, the entire chain of encounters is highly unusual. Interstellar objects, by their very nature, are expected to arrive from random directions and at steep scattered angles. They are falling into our solar system's gravity well without any long-term guidance. Their paths should typically slice through our system at odd angles before the sun's gravity flings them back out into deep space. 3i Atlas breaks this expectation in a fundamental way. Its motion stays remarkably close to the ecliptic plane. The ecliptic is the flat, disk-like region where most of the planets, including Earth, orbit the Sun. For an object entering our solar system by pure chance, aligning with this specific plane is statistically difficult to explain. It's like throwing a random dart at a spinning globe and having it land exactly on the equator. The timing of these planetary encounters adds another layer of intrigue. By approaching multiple planets in a relatively short window of time, The object increases its opportunities for gravitational influence, energy exchange, and potential orbital adjustments. This does not mean the object is being actively controlled, but it does suggest that its path is unusually well positioned to interact with both the inner and outer planets of our solar system. Then there is the question of its origin direction. When astronomers traced the incoming path of 3I Atlas back through space, they found that it appeared to originate from a region of the sky linked to one of modern astronomy's greatest mysteries, the famous WOW signal detected in 1907. The WOW signal remains one of the strongest, most structured, and completely unexplained radio bursts ever recorded. Its source region has been the subject of intense debate for decades. Now, we must be extremely careful here. This alignment does not prove a connection. No serious scientist is claiming that this object is the source of a radio signal from over 45 years ago. However, the coincidence is difficult to ignore when it is added to the growing pile of other anomalies. On its own, an odd trajectory could be dismissed as a statistical fluke or a rare gravitational alignment, but when you combine it with a stable, predictably rotating core, precise and controlled jets, a chemical composition unlike any known comet, and an energy output that defies explanation, the orbit starts to look far less accidental. Each planetary pass offers a chance to gather more data, but it also deepens the question of why this particular object keeps arriving exactly where our planets happen to be. Scientists remain cautious, as they should. They emphasize that gravity is complex and can produce strange and unexpected paths, especially when the gravitational pulls of multiple bodies are involved. Still, the odds against so many unlikely features appearing together in a single object begin to stack very quickly. At a certain point, invoking probability and chance alone stops being a satisfying scientific answer. The path of 3I Atlas forces us to confront a simple but uncomfortable thought. If this object were only a natural fragment wandering aimlessly through interstellar space, why does its journey seem so perfectly placed within the architecture of our solar system? This sets the stage for the final piece of this puzzle, because the future encounters of this object may finally decide whether this path is a mere coincidence or something far more significant. We have arrived at the most uncomfortable coincidence in this entire story. As we mentioned, when scientists traced the incoming trajectory of 3I Atlas, they found it points back toward a very specific region of space, a region that happens to overlap with the area linked to the famous WOW signal. Let's briefly revisit what the WOW signal was. In 1977, the Big Ear Radio Telescope in Ohio detected a brief but incredibly powerful radio burst that lasted for just 72 seconds. It had a strength and structure that closely matched what scientists at the time expected an artificial, non-natural radio source to look like. It was so startling that the astronomer who found it, Jerry Amon, circled the data printout and wrote, "Wow!" in the margin. But it never repeated. Despite decades of searching, that signal has never been detected again. Researchers have debated countless possible origins, from rare astrophysical events to unknown terrestrial interference, but none have ever been confirmed. The source region of the WOW signal remains one of the most tantalizing and mysterious coordinates in the sky. When the path of 3I Atlas was reconstructed, its apparent point of origin lined up with that same general direction. Again, we must stress that this does not prove a direct connection. However, a coincidence of this nature gains weight when it appears inside a much larger pattern of anomalies. By itself, a directional overlap means very little, but when you place it alongside the object's unusual motion, its controlled activity, its strange chemistry, and its unexplained energy budget, it becomes harder to dismiss so easily. Interstellar objects are expected to come from random points in the galaxy. Their arrival direction should be scattered all across the sky with no particular preference. This statistical expectation is what makes any alignment with a well-known, pre-existing anomaly so interesting, even if it remains inconclusive. It invites a deeper look rather than a quick dismissal. Researchers are handling this part of the discussion with extreme care. They rightly emphasize that space is vast, and coincidences are bound to happen. The WOW signal could very well have a completely natural source that we simply haven't identified yet. At the same time, the process of science advances by noticing when multiple, rare, and seemingly unrelated features intersect, not by ignoring them. What matters most is how this final detail fits the overall tone of the entire case. time and time again, 3i Atlas has brushed up against the boundaries of what science considers likely or even possible for a natural object. Its rotation behaves with unexpected order. Its chemistry resists simple classification. Its energy output raises fundamental questions about its power source. And now, its apparent point of origin echoes one of astronomy's oldest and most profound unresolved signals. None of this proves intent or artificial design. What it does prove, conclusively, is that this object does not sit comfortably inside any single box we have. Every time a clean, simple explanation seems possible, another layer of evidence adds tension and complexity. So the final issue becomes unavoidable. If chance alone is responsible for all of these anomalies, then how many coincidences should we be expected to accept before we begin to ask whether something deeper, something more fundamental, is at work here? The story of 3i Atlas has now brought us to a crossroads of scientific explanation. Every layer of evidence we have examined tonight points to an object that refuses to fit our clean, established labels. Let's summarize the chain of evidence. We have a structure that remained intact when it should have disintegrated. We have activity that followed predictable rules and appeared controlled, not chaotic. We have a scientific prediction made in advance that matched reality with stunning precision. We have a chemical makeup that broke the known rules for comets, showing high metal content and very little water. We have an energy output that exceeded the limits of its visible material, creating an acceleration that we cannot fully account for. And finally, we have a path through our solar system that crossed unlikely and significant coordinates, including an apparent origin that aligns with a historic astronomical mystery. Each one of these clues taken alone could potentially be explained away as a fluke, an anomaly, or a gap in our current knowledge. Yet when you view them together, they form a coherent and powerful pattern that forces science to slow down, to question its assumptions, and to reconsider what is possible. The path forward will be defined by more data. Upcoming observations in ultraviolet light from Hubble and new measurements from other missions may finally settle this debate. They may reveal a new, natural explanation that accounts for all these strange properties, or they may push us even further towards something entirely new. This brings us to the ultimate question that this entire body of evidence demands we ask. It is a question that matters to everyone, not just scientists. If 3i Atlas is not just a comet, what do you think we are really witnessing? We encourage you to share your theories and thoughts. The investigation continues, and we will be here to report on what comes next. Thank you for joining us.